Hi, welcome to today's astronomy video about white dwarfs and the future of our Sun. This is a nice overview of the nearest objects to the Sun. Yellow star Sun. Closest object is a red dwarf Proxima Centauri. It is part of a triple star system. Then you got here Luhmann 16A and B. That's a binary pair of brown dwarfs. Many stars are red dwarfs. And at the top you can see Sirius, and here Procyon. These are both binary systems that contain white dwarfs. This is a comparison of a white dwarf compared to a normal star. Here we soon see the white dwarf in the background. White dwarfs are typically Earth-sized. Their maximum mass is 1.4 solar masses. A typical surface temperature is 10,000 Kelvin. They can't do hydrogen fusion anymore because they don't have hydrogen in the core. They are opaque. That's why their cooling takes more than 1 billion years. This is an overview of the life cycle of stars. 97% of the stars are here, and they will become white dwarfs. The Chandra limit of 1.44 solar masses defines the upper limit of the mass of white dwarfs. Above the limit, there are the neutron stars, and there's another limit of 2.0 to 2.2 solar masses, and above that limit, the stellar mass black holes. This is a close system, binary system Sirius. It's at 9 light years distance. The big star is an A star, Sirius A. It has twice the mass of the Sun. The small object is the white dwarf at 8 to 32 AU. 1 AU is Earth-Sun distance. It has a mass of 1 solar mass. And the orbital period of this white dwarf is 50 years. Here's another image of Hubble from the system Sirius A and Sirius B. Sirius A is also called dog star. Sirius B is here, the white dwarf, called the Pup. It was discovered in 1844 by German astronomer Friedrich Wilhelm Bessel. It has a luminosity of just 6% of the Sun. Surface temperature is 25,000 Kelvin. And the age of the system is between 220 to 240 million years. This is called a winter triangle. This at the top left is Procyon. This is Betelgeuse, a red supergiant. And at the bottom, that's the big star Sirius. This is the system Procyon. It's a binary at 11.5 light years distance. In the inner orbit, that's the big star Procyon A. It's a massive star, F star, with 1.5 solar masses. Surface temperature 6,500 Kelvin. In the outer orbit, that's Procyon B, that's the white dwarf at 9 to 21 AU. It has 60% of the Sun's mass. Its surface temperature is 7,740 Kelvin. Its age is 1.4 billion years. And it must have been formed from a big star with a mass of 2.6 solar masses. This is an overview of the internal structure of white dwarfs and of the types DA, DB, DO, and PG1159. All these white dwarfs have one thing in common, that's the core it consists of carbon and oxygen. The DA type has a hydrogen and helium layer. The DB type has only a helium layer. The DO type has a helium ion cation layer. And there's this group PG1159. It is named after a pre-degenerate white dwarf that was discovered in the Palomar Green survey of UV excess stellar objects. The white dwarf can't fuse hydrogen atoms, but it is stabilized against total collapse by electron degeneracy pressure. This works at masses below the limit of 1.4 solar masses. And the electron degeneracy pressure is a consequence of the Pauli exclusion principle from quantum mechanics, which says that half-integer spin particles can't have identical state. This is how PG1159035 or GW Virginis would look like. It is at 1,800 light years distance, at 63% of the sun's mass. And this object is in a transition from a normal star to a white dwarf. This is the light curve of PG115035. And you can see from here to here, that's 1 hour, about 7 peaks per hour. And these peaks result from the gravity wave pulsations in the inside of this white dwarf. This white dwarf is a vampire star, so many stars in the universe are part of binary systems, so this type is quite common. This white dwarf takes matter away from its companion. This destabilizes the white dwarf, and the result is a type 1a supernova. That's the explosion of this white dwarf and destruction of the white dwarf. This supernova is essential for life because it provides heavier elements to space, and the following generations of stars and planets have a higher metallicity. And metallicity means the percentage of elements other than hydrogen and helium. And there's a hypothetical variant, type 1AX supernova. This could be 5 to 30% of this type of these supernovas. And this 1AX supernova, only half of the white dwarf is destroyed, and the product is a zombie star. This is a blue dwarf. This will be formed from red dwarfs. These are M stars, but only from the light M dwarfs, with 6 to 25% of the mass of the sun after they run out of hydrogen for the fusion. 75% of all stars are M stars, red dwarfs. But the minimum main sequence lifetime of a red dwarf is 1 trillion years. So the universe is just 13.8 billion years. So blue dwarfs are not formed yet, and they will eventually also become a white dwarf. This is how the sun would look like in 10 billion years. Of course, Earth will not be habitable in 10 billion years. The white dwarf sun will have half of today's solar mass. The other half will be distributed in space, will be available for future generations of stars and planets. This white dwarf will likely have a new disk. So in theory, there's a potential for a second generation of planets and potentially even for life. This is one white dwarf with a planet. That's WD1856 plus 534. Is located at 80 light years from Earth. It is part of a triple star system with 2 red dwarfs, with each about half a sun's mass. The age of the system is 5.8 billion years. This white dwarf has a companion, this Jupiter-sized exoplanet WD1856 plus 534b at 0.02 AU at a very close distance. Its mass is 5 to 14 Jupiter masses, so if it has 14 Jupiter masses, it is not a planet, it's a boron dwarf. And the current theory for this system is a planetary migration theory. There's another system, a white dwarf planet, WDJ0914 plus 1914, as a Neptune-sized exoplanet at just 0.07 AU. And the exoplanet loses atmosphere into the disk of the white dwarf. This is a black dwarf, and they don't exist yet. They will be formed in 10 to 15 years from white dwarfs, because it takes so long for white dwarfs to cool down to 5 Kelvin. That's about 10 times the age of the universe. That's why they don't exist yet. And black dwarf, there could be further evolution of these objects, and this depends on the stability of the proton, if it's stable or not. And there's potential fusion to iron in 10 to the 1100 years. Other possible scenarios for white dwarfs are cannibalization and evaporation. This could lead to a helium planet or a diamond planet. This is a nice animation of the heliosphere of the sun, and outside of the heliosphere, that's the heliopause. The spacecrafts Voyager 1 and 2, Pioneer 10 and 11, are in the outer zones of the solar system. And this is the golden record of the Voyager spacecraft. It contains enough information about the position of the solar system for intelligent species to figure out. And the Voyager 2 spacecraft will be within 1.7 light years of the star Ross 248 in 42,000 years. And it will be within 4.3 light years of the star Sirius, system Sirius, in 296,000 years. And that was today's video about white dwarfs. You can check out the links to the scientific articles. Thank you for watching. Have a nice day. Bye-bye.